Hi, I'm Yongsong Zhuang from National Taiwan University. I'm going to present our work, SpeechBERT, an audio and text jointly learned language model for end-to-end spoken question answering. This work is done by me, Jiliang Liu, Hongyi Li, and Linshan Li. Most of the question answering systems are based on plain text document. We make the machine read a document and then input the question to the machine. It will output the answer. However, in reality, there is much more information hidden in audio than in text. And it is much more difficult to search in the audio content. That is the reason why we need a spoken question answering system. Currently, there are two pipeline stages to solve the spoken question answering task. The first step is to convert the audio into text using a speech recognition system. The second step is to put this text into the text-based question answering model. However, in the study conducted in INTERSPEECH 2018, it was found that the performance of the same question answering dataset with correct text and speech recognition transcription are very different. The performance is decreased by about 20% if the model takes ASR transcription as input instead of the correct text. The main reason is that speech recognition errors greatly affect the QA model. And no matter how powerful the QA model is, it is not possible to recover these errors. To avoid this error bottleneck, we want to build an end-to-end system that can perform question answering directly on audio signals. In the end-to-end spoken question answering model, we have the audio document and a short question in text. Our model will predict the time span of the answer directly according to the audio signals. Before starting to design our end-to-end question answering model, let's first understand how text-based question answering is currently done. Most of the current state-of-the-art models are based on BERT proposed by Google in 2019. The core concept of BERT is to perform pre-training before starting to fine-tune on QA dataset. In pre-training, we first make the model learn to recover 15% of the words that are masked out based on the contextual information. After pre-training, the model will have the basic ability to understand language. And then we fine-tune the pre-trained model on QA datasets. So, our idea is to borrow the concept of BERT to create a speech version of BERT. We pre-train our model on audio data, and then fine-tuned it on spoken question answering dataset. The difference is that the input of our model is audio signal, so it can be trained in an end-to-end manner without the error bottleneck. Let's talk about how do we feed the audio signals into the model. Because the audio signals are very noisy, it is hard to capture the semantic information inside. Thus, here we segment the audio into audio word segment, according to the force alignment results from an off-the-shelf ASR model. After that, we train an autoencoder to capture useful information in the audio by minimizing the reconstruction loss. And we align each audio word with corresponding embedding from the input layer of BERT by minimizing the L1 distance between them. Finally, we can present each audio segment with a vector that are consistent with the embedding space of BERT. Now, given the audio signal input, we can segment the audio first and encode the segment with our audio encoder to get the representations of each audio segment. And the representations of each audio segment can be treated as a word embedding and feed into our SpeechBERT model. For the text input, we can just use the word embedding layer to get the word vector of each word. These two types of vectors are concatenated and fit into our SpeechBERT model. In pre-training stage, we mixed out 15% of the input vectors and make the model learn to recover the corresponding text of the masked audio. Here, we use the pre-trained weight of BERT as initialization of our model. After pre-training, the model will have a basic ability to understand the audio dataset. Then, we take the pre-trained model, fine-tune it on the spoken question answering dataset, and make the model predict the start and end position of the correct text. Let's illustrate more on how we get the word boundaries. In training time, we have the ground truth transcriptions of the audio, so we can just use the ground truth transcriptions to run false alignment and get the word boundaries. However, in testing time, we cannot access to ground truth transcriptions according to our experimental setup. Thus, we run the ASR model first to get the hypothesis, and then use the hypothesis to run false alignment. Although there are recognition errors in the hypothesis, the word boundaries founded by false alignment are usually according to some real words. Because our model only takes the word boundaries information as input instead of the ASR transcription, it will not be affected too much. We will prove this claim in our experiment. In the experiment, we use the SQUAD dataset. In the previous work in 2018, Spoken SQUAD is proposed as a speech version of SQUAD. However, in Spoken SQUAD, all of the questions with recognition errors in its answer spans are dropped because they are too difficult. So, Spoken SQUAD only contains a subset of original SQUAD questions. The other questions, here we call them SQUAD lost, are the questions with ASR errors in its answer spans. We use both of the subsets in our experiment. And these two subsets contains comparable data size. For simplicity, we call Spoken SQUAD as correct set and SQUAD lost as error set in the following video. In the main experimental result, we compute the time-level F1 score and the audio overlap score, AOS, to evaluate the performance. We found that on the easier correct set, the accuracy of the pipeline BERT model is higher. But on the more difficult error set, our SpeechBERT can significantly outperform the pipeline BERT. And the sum of these two subsets also shows the advantage of SpeechBERT. Then we show further experimental results on the correct set, which our SpeechBERT did not outperform pipeline BERT model. The first part of the results are pipeline QA models. Here we can either train these QA models on the ground truth transcriptions or the ASR transcriptions. Then we can test the model on the ground truth transcriptions or the ASR transcriptions of the testing set. And we can see the performance gap in the different testing set. The performance of spoken data is much lower than that of the text data. And the best pipeline method is BERT, trained on ASR transcriptions. The pipeline result in the previous page also use this method. The second part of the results are end-to-end models. We train the models on audio with ground truth alignment and test the models on the audio with ASR alignment. The third part of the results are on symbol models. We can either on symbol BERT with SpeechBERT or on symbol 2 BERT trained with different random sets. First of all, on the correct set, our SpeechBERT can outperform the previous method other than BERT. Although SpeechBERT has not yet outperformed BERT on the correct set, our model made a great improvement when we on symbol BERT with SpeechBERT. The improvement is significantly larger than that of on symbol 2 separately trained BERTs. It means that our model and text-based BERT have learned very complementary information, thus the on-symbol result improves so much. And this result is current state-of-the-art score on spoken squad dataset. We have also done ablation study and proved that if we skip the pre-training stage, the performance of SpeechBERT will drop a lot. In addition, we want to know how much will the better word boundaries affect the model's performance. Thus, we segment the audio by false alignment using the ground truth transcription, which is not accessible in our experimental setup. We show that it would bring improvements about 2%, but the improvements is not very huge. So we infer that the segmentation quality is not a critical factor in our model. Finally, we grouped the questions according to the speech recognition word error rate in the whole testing set. We found that when the word error rate is less than 40%, the pipeline model performs better. However, our model is able to take the advantage of its end-to-end architecture when the recognition errors was greater than 40%. This is a brief introduction to our work. Further detail can be found in the paper. Thanks for listening.